I told you there is no way, and I was so happy that it's actually a nice day today. So let me remind you a little bit about what we were doing last time. And there are a few more things I want to tell you about materials behavior before we go to boundary conditions. And expect to have a class exercise next week. I actually was planning one for today, but decided to do more examples. So it's a nice day. There is no reason to make it. Yeah. Anyway, so last time we talked about isotropy. So remember the way we kind of discussed it was that the elasticity tensor would be rotation invariant. So try to see if you can write it down. So what happens if you have a elastic tensor MNPQ? So like that, if you rotate it. So these are direction cosines matrices. You are going to get the rotated version, and when we say that it is invariant, we mean that if you rotate it, if you transform it, there will be no difference. You are going to have the same elasticity tensor, and that's the definition. That's one way to look at isotropy. And what I told you was that the general form of an isotropic elasticity tensor will have this form that you kind of dealt with it in your homework, right? So alpha, beta, and gamma are constants, and you have these Kronecker delta functions. Right. So if we have linear elasticity, what happens? So I kind of jumped to what would be the stress-strain relationship, but let's try to do this together and see, kind of warm up in the beginning of the class. So if we have linear elasticity, what would be the formulation? It's very simple, right? Sigma is sigma ij it's linearly related to a strain E. So if you substitute the above, see what are you going to get. I feel like it's important that you become more and more comfortable with the use of index notation. It's very simple, so it shouldn't take long. Just substitute the general form, or even you don't have to. If you can see it immediately, just use the Kronecker delta function, this substituting operation, and try to see how what you are going to get. So the general form alpha plus beta plus gamma, if you substitute it in the linear elasticity relationship, how does it look like? Let me see what you are doing. This is kind of a reflection of this class exercise where I thought everything was very simple, and then turned out that there's a quiz.
I was just saying once today.
Today is a nice day. Anyone deserves a quiz today.
We'll just assume this would be 2. As you try.
Put the terms together. Okay. So remember that delta, you just use it as a substituting operator. So if we apply the first term, delta ij and delta kl, the delta kl, ekl will be ekk or mm or nn, whatever you want to write it. And then delta ij is going to be there. So I write this and since many of you did this mistake, we cannot have more than 2 indices repeated. If you have 4, you have to use something else. You can't have ekk, ekk, ekk. This doesn't mean anything, right? So if and then for the other 2 terms, all you have to do is really k and l are going to substitute, become I and j, right? So then if I collect the terms, then I'm going to get beta plus gamma eij. And if you recall from last time, this form should somewhat look familiar to you. This is the form that kind of I magically arrived at. I just didn't use alpha. I used gamma and not gamma, lambda, and instead of beta plus gamma, I use 2 mu, right? So basically, linear elasticity is just a special case of that. Don't be confused. So if you look at this alpha plus beta plus gamma, that's the general form, and this alpha and beta and gamma, they mean something physically when we look at linear elasticity. So that's one way we talked about isotropy. It turns out that you can define isotropy in one other way too. So there is a theorem which I don't give you a rigorous proof for that, but for defining isotropy, if you consider the principal directions for the stress tensor. So you have the stress tensor, the strain tensor, both of them are symmetric tensors. I think this is obvious to all of us. And second order, so they have real valued eigenvalues, remember? And then we have eigenvectors which form what? What do the eigenvectors of a symmetric second order tensor form? An orthonormal basis. So all of that is kind of implicitly implied here. Suppose G1, G2, G3 are eigenvectors of tensor E such that they form an orthonormal basis, and we know that this is very possible because of the properties that these tensors have. In the realm of linear elasticity, the material is isotropic if and only if G1, G2, G3 are also eigenvectors of sigma. So this is kind of an important and interesting thing to notice. That means in plain English that the principal directions of a strain and stress tensors are aligned. They are the same. So I write the English version too. That is the principal directions. And you know that I'm using this term just to make you remember. That's another term for saying the direction of eigenvectors of a stress and a strain. Are identical. So I confess that I wanted to give you this as a quiz today. So it's very easy to show. So I recommend that you show it for yourself at home and expect it to be a part of the quiz next week. How else I can? So just, it's very simple. It's very simple, but try to just show it for yourself and see that it is possible to show. So another thing before moving from chapter 4 to 5 is talking a little bit more about these elastic constants. So if you remember last time, we talked about Lamè's constant, which I just showed you, lambda and mu. But we also talked about some other pairs of elastic constants. You remember the very famous one that you all have seen? What do you learn first in the first strengths of materials? You don't learn about Lamé constant. Don't tell me that you learned Young's modulus and Poisson's ratio, right? So we also learned about this. And then towards the end, what else did we talk about? Shear and bulk modulus. So I used kappa and shear modulus, which is the same. So it turns out that we can bound the values of these constants also. And for that, we need to borrow a little bit definition from a strain energy again. So we did a little bit of a strain energy last time to show you the symmetry, one symmetry in the elasticity tensor. I have to do a little bit more strain energy here before really talking about the strain energy in detail. So we all know what a strain energy, I think pretty much it should be something familiar to you. How would you define the strain energy if someone asks you what is the strain energy?
Energy stored in deformation.
Yeah, that's a good definition. So I have written it in terms of work. So work done by internal forces, which internal forces are actually, they are more like, sometimes people call them stresses. But you know that a stress and force are two different things. So strain energy, I think it's obvious. I just write one definition here. So work done internally. I think what's important here is that this is for internal forces, not by external forces, by a body as it deforms. And we used the symbol U last time. I used the same. And in general, basically you can just write an integral. You have seen this in other classes. And what you get is a strain energy density, so a strain energy per unit volume. Because we are not really looking at force and displacement, we are looking at the stress and the strain. So now in the realm of elasticity, so for a linear elastic material, we know the relationship between a stress and a strain. I'm going to substitute that. U would be, and sinceCijkl is constant, so we are homogeneous, we are considering homogeneous material. It will look like that. So I'm just replacing sigma by its definition. So when the material is isotropic, I just showed you again what would be the relation between a stress and a strain. Basically, the strain tensor would, the elasticity tensor would be much simpler. And it's a good exercise to kind of, I'm not saying to memorize this, but to get used to it. Because we are going to see this very many times from now on. So if you substitute this, you can write the energy in this form, just in terms of a strain. Now, it turns out that it's useful to write the energy, to partition it between the energy which is responsible for volumetric change and the energy which is responsible for change in shape. And we learned something about the strain, right? And I think the class exercise really emphasized that last time, that you can separate the strain tensor so into the deviatoric and spherical part. So what I want to write the strain energy into two parts. One part which is in terms of E hat and a part which is in terms of E tilde. So one part which has something to do with volumetric change and the other which doesn't. So quickly, so recall that we defined E tilde and E hat such that E tilde was the part which has something to do to the volumetric change, delta ij, and E hat is the rest. And these are tensors. In your work, sometimes I saw that. Don't forget, even these two parts are tensors. They are not vectors or anything else. You are just separating a tensor into two. And now you all know that we have this relationship, right? Somewhat through a hard way. I guess now I don't have to say it can be shown. You all know that this is the case. And the physical interpretation is that it is like in a higher dimension, you have inner product. So if the inner product is 0, it means that you have some sort of orthogonality. It doesn't mean that they are vectors, but you have orthogonality, which means that they are kind of independent from each other. And that's what you expect. One is responsible for volumetric change, and the other just change of shape. Now, with all of this kind of preface, I want to, maybe I actually move to the next slide because we are going to need this. That you can write U in two parts. One part has something to do with the volume change, and the other part, it doesn't. And I guess it's useful to remind ourselves what this means. The magnitude squared, this is what it is. So why are we doing this? I started telling you that I need to tell you a little bit more about the strain energy because I want to put some bounds on the elastic constants. And this is where I wanted to arrive. So let's look at this equation. So we have two terms, and the strain parts, they are squared, right? If you have a stable physical process, so for a stable physical process, if there is no force, no strain, no stress, what do you expect in terms of strain energy? What is the minimum strain energy a system can have? What do you expect? If you have a body, if you have something here, you don't do anything to it, what should be the energy you think? A strain energy. We are talking about a strain energy. It's 0, right? So if the process is stable, so that the system would respond as you would expect, if you do something to it, if you deform it, all you can do is to increase the strain energy from 0 to a positive value, right? So what I want to get to, without going to a lot of mathematical jargon, is that U is always greater or equal than 0. And since the two parts that you see in terms of a strain tensor, they are both squared and they are positive, what does it tell us? I'm sorry. Exactly. So then lambda, so the two constants have to be greater than 0. The two parts. And then in terms of E and Poisson's ratio, that implies that E's should be also positive, but Poisson's ratio can vary between -1 and 0.5. And in terms of kappa and mu, kappa has to be positive, mu also has to be positive. So in the processes that we deal with, when everything is stable, stability is kind of, it corresponds to having positive, some of them positive, and then you see Poisson's ratio, for example, could have a range. Yes, I kind of expected this question. So yeah, there are materials which can have negative Poisson's ratio. So they are called anti-rubber. These are not the materials that we normally see. They are called anti-rubber, and a lot of them are also what you would call metamaterials. Some form of foams are like that. So what does it mean if a material has a negative? I wish I brought a video. So there is some science paper where they are showing a foam which has a negative Poisson's ratio, and they have actually built it. What does it mean if a material has negative Poisson's ratio physically?
If you stretch it from one direction, you also increase in gravitation.
Exactly. So they have, so these are kind of foam, sponge kind of structures inside. Imagine, I don't know the name of that. It's kind of origami. I don't know the name. It's like a honeycomb kind of a structure that if you stretch it also, because I looked at the video, it also stretches on the other side. I thought about bringing it to the class, but we are so much behind that I was like, I cannot show you. But if you are interested, let me know. I'll send you I can send you the link to that science paper. So it's possible to have materials which have negative Poisson's ratio. But most of the materials that you have seen, they are more rubber-like. So the reason they are called anti-rubber is because they are behaving opposite to what you expect. If you stretch a rubber, what happens? It thins out, right? So they actually increase in size in the other direction. Now it's very fashionable to use the term metamaterials, so you try to engineer materials which have some exotic properties, including negative Poisson's ratio, because it can be useful for some applications. Okay, so this is all I wanted to tell you about linear elastic materials that was left out. And with that, we can kind of start. Any other questions before we move? We can start with what we wanted to do, and that's the boundary value problems. So linear elastic boundary value problem. So now we have a bunch of equations. Last time I wrote down some equations, but our equations were not complete. We didn't have material behavior. So let's write down and see how many equations we have. This tends to be very important. What does the balance of linear momentum give us? So let me write it. Number of equations. And this is chapter 5 now. What equation does it give us? Prabha? Did you want me to hear it or no? What is the equation it gives us? This has to be second nature to you. That's the class of equations. No, please tell me. Del sigma. Yes, correct. It's you remember the Cauchy law? You should be now kind of be able to write it on your own. So I write it like this in index notation. How many equations is this? It's 3. I call this equation number 1. And then, again, strain kinematics. What is the What is the important equation? It's one of them. So strain kinematics, we can have, let's call this 2A. I don't know how I didn't do it, but here, but it would be good to call it 2A or 2B. One is the compatibility. And I told you that how many independent? 6. That's right. So this is when I have let K is equal to L, and this is 6 equations. I'll tell you in a moment why I have 2A and 2B. What is the other, what did we learn in strain kinematics? All the things I drew, all remember the squares which were rotating and all that trouble? Then we separated to symmetric, skew symmetric, and one part was infinitesimal rotation, the other part was a strain. Exactly. The strain is the symmetric part of the displacement gradient. I want to make you such that you just never forget these things, right? You should learn them as if they're second nature to you, because this is a course which is a foundation of a lot of other courses. So you kind of need to learn that. So remember this? And how many equations is this? 6. I have to put a word or between the two, because compatibility equation is kind of, it's very related to that equation above. If a strain field is given, the compatibility equation would be trivially satisfied, right? It becomes very important if you are solving things in a stress. So in elasticity, we have 2 ways of solving problems. One is displacement formulation, the other is a stress formulation. Now, if you are solving everything in displacement, compatibility equation would be automatically satisfied. If you are solving things in a stress, which you will see soon, then you need to use that instead. Because if you use compatibility, that already satisfies the above equation. So these are not independent from each other. That's why I use the word or. And last time we learned another equation for linear elastic isotropic homogeneous materials. A stress-strain relationship. So let's write that also and see how many equations we got. Sometimes this is called constitutive law, right? And this also has to be something that, you shouldn't look at the reference to write this. This you should know, right? How many equations are these? Also 6. We learned about all the symmetries, etc. We have 6. So if you sum everything up, how many total equations do we have? 15. 15 equations. So I write it because it's important. So linear elastic boundary value problems are governed by equations. Now, how many unknowns do we have? 15. What are those? Exactly. So Typically, the unknowns, we use a bracket like that. We have ui, we have sigma ij, and we have eij. This would be like the unknowns. And if we find a solution to the boundary value problem, it means that we found this triplet that satisfies equations 1, 2, 3. I forgot to put 3 here. So what we are looking for is so these are unknowns. So this triplet is called a solution if these fields, these are all fields, right? Stress strain fields, satisfy 1, 2, 3. So are we done then? We have the 15 equations, 15 unknowns. Perfect. We can go ahead and solve the problems. What is missing to define a boundary value problem? Sorry, did you have a question?
So why did you not include the concept of the compatibility equations? So you did not produce any extra information other than
I'm not sure. Are you talking about equation number 3?
Yeah, or the compatibility equation.
The compatibility equation is 2b. So it is either that or the strain kinematics. I'm sorry, what?
So they are equivalent?
They are not equivalent. So if you are using displacement formulation, you have to typically use the first equation, 2a. Right? If you're using displacement formulation, compatibility equations are automatically satisfied. They're not going to give you any extra equations. If you're using the stress equations, on the other hand, you need to use them because this is not the case.
So what is the difference of compatibility equations?
Well, this is your first time coming to the class. So compatibility equations are necessary and sufficient conditions that you have a single valued, a continuous displacement field. And your boundary has to be simply connected. If it is multiple connected, there are some tricks to also use that. But that's the function, right? If you start with a displacement field, they are trivially satisfied because you have displacement field and you use the derivatives, and this is going to be always satisfied. So it's not going to give you an extra equation. Does it make sense? I'll be happy after the class to tell you more about it. But we already have talked about it. This is now just everyone has heard about compatibility equation oftentimes that they don't want to hear about it anymore. And they have in their homework too, right? The 2 first questions, if you have seen, are related to compatibility equation. Okay, so going back to the question I asked you, are we done? 15 equations, 15 unknowns, everything looks very, very good, great. What else do we need? Boundary conditions. So we need to have boundary conditions. And this is what I want to talk about in detail. These are called boundary value problems. And solving field equations, as you have seen probably in other classes, you always have to have some sort of boundary conditions. And so let's talk about boundary conditions. So a boundary value problem, I have to tell you one more thing. What type of equations are these? Exactly, these are a bunch of partial differential equations. So if you, boundary value problem by definition is partial differential equations plus boundary conditions. The name has boundary in it. Okay, so there is no more trying to convince you that we need boundary conditions. And what I want to do is to tell you the classes of boundaries, and I like us actually to do some real examples because I feel it is necessary. So we have three important cases of boundary conditions, or the ones that we consider here. We consider three cases of boundary conditions. One. Case one is pure traction. What does it mean? It means that you have this body, and the boundary is obvious, right? What the boundary is, we always use this for boundary, and you have some traction applied to this boundary. And with traction, if you remember, you always, because traction is force per unit area, so it's applied on the boundary, so you always have to use a unit normal vector to actually orient your boundary. So that's what n is. Let me see what else I'm missing here. I use s for the boundary, not dB here, because I've taken a note for myself. Book does that. So I use just s, not what we usually do. So the boundary condition is simply written as, in terms of traction, so all when we say pure traction, it means that the whole boundary, what you specify, is only traction. And in component form, this looks like this. And the bar on the top means specified. Okay, so you kind of can guess what comes next. What is important here, and I mentioned it last time, is that we don't have a stress boundary condition, it's traction boundary condition. Okay. But you see it in the examples. Number two, we have pure displacement. So again, this is boundary, there is S, and you specify that you specify some displacement, prescribed displacement. A very simple example of this is what? When you have what type of boundary conditions? Like fixed boundary conditions, right? Wherever something is fixed somewhere, you just specify displacement and then everything is good. One important one is a mixed boundary condition. And you can guess what mixed here means. It means that a part of the boundary you have traction specified, a part you have displacement. Try to so this is one part of the boundary, ST, and this is SU, and consider that SU, the union of SU and ST, is S. That means that together they make up the entire boundary. And what is less obvious, and I have to tell you more about it, is that they are separate from each other. like their intersection is, there is nothing in it. They don't overlap, yes.
So at the intersection
At the let's look at the examples. Yeah, that would be useful to look at the examples. So then I didn't foresee this question. I knew that Thomas is going to ask me about the negative Poisson ratio. I don't know why. When I was thinking about it, I was like, he's going to ask, but I didn't think about this. I'm writing it a little bit. Yeah. So this is saying that on one part you have displacement, on the other part you have traction. I have to add here something, and that is that you have seen, I'll show you an example, that there are cases when on the same boundary you have specified both traction and displacement. This is sometimes possible, but whenever you have done it in different directions, perpendicular directions. So when you think about it, think in terms of components, right? So it is possible. And this is the kind of question I expected to get when I show you, because you are familiar with boundary conditions, that you can have at one point two boundary conditions, displacement in one direction, traction in the other direction. But you cannot constrain a strain and traction in the same direction on one point. And whenever you constrain displacement, you can obtain traction and vice versa. This is kind of a basic rule of boundary condition. Gerald, this is obvious. So wherever you constrain displacement, you can calculate a stress. And wherever you constrain, from the equations, wherever you constrain traction, you can calculate displacement.
Just to clarify, you're saying that if you do that, it's redundant, right?
Oh, you cannot do that. No, it is because then it will ruin your, if you can calculate it, so if you specify it, it's going to be, you cannot do that, right? Because your equations are going to give you possibly a different number. Right? Does it make sense what I'm saying? So you actually can, you will obtain it. And if you prescribe it before, then, and if it is different, the value from what the equations are going to give you, you are in trouble. You cannot do that. Yeah. We try to make things a little bit more tangible for you. And if you have taken strengths of materials like elementary classes, you have also seen another boundary condition that I just tell you in passing, and it's called Robin boundary condition. And this is when you don't specify either traction or displacement, but you specify a relationship between the two. If I draw one example, you all say yes, you have seen it. If you have taken any class in strengths of materials, you may have dealt with a situation like this. At the end of the beam, the fixed end clear, it's a displacement boundary condition. At the end of the beam, what is the boundary condition? It's a linear relationship between traction between the force P and the stiffness of the spring through the displacement of the beam. So you have a mixed kind of situation, but a different kind of mix than I was explaining to you before. We don't really deal with this here, but it's good to have it somewhat written. So now, instead of moving forward, I thought it would be good to, I've written down the equations, it would be good to make them more tangible. And let's do a few examples together. So, example number 1. So I give you this, there is it's an object, let's call it an object. What is wrong with me? So let's just first draw the object, that would make better sense. On one side, it's fixed, and on the other side, you have this force, so this is force per unit area. And this side is, the length is A, this side is B. X, Y, so basically you can use 1, 2, but it's the same as X, Y here. So what type of problem is this in those 3 categories? Number 4 is kind of an exotic. Which one is it? It's a mixed boundary condition, right? Because you have a fixed boundary condition to the left, and then you have traction to the right. So try to formulate that based on what I have given you before, and ask me questions if you have trouble translating that rotation into a real problem. I want you to write the boundary conditions for this problem. There are 4 boundaries. You are given this object, which is a kind of a square. Imagine it's a kind of a rectangle, and it has 4 boundaries. So what are the boundaries? Origin is up to you. We don't need to know that, but yeah, it's up to you. Careful about notation. It's all about notation. This class. It's not. You cannot just write like you have to be U1, UX,
If we're
You have something for the space of material practically elasticity. Try to kind of worry about it. You need this one transform for the way So I think it was very good idea to, I thought so, because when you see the formulation you can follow. It's sometimes hard to bring that into the practical. What is that? Okay, let me then go through this. Let's go through this together, and then hopefully we'll have time to do one more. So this is a mixed boundary condition, right? So let's look at first the fixed n, which is simple. So we can say that so I've used this as the origin to orient myself for we can say that in that wall that right, some of you have written this is also okay. That's easy. What did we say about, now let's look at the other side, which is more problematic. What did we say about that? We said T1, how do you write it? Sigma 1 1 n1 plus sigma 1 2 n2. This is, everything is 2D. What is n? What is n for side, for the other side? Oh, I should write the x and y so you know what side I'm talking about. So let's write things nicely. So if we take x equal to a and y, right? And 1 and 2 are x and y, so you can use either one. For this problem, things are simple, but it's important to use the right form, because if things become complicated, then you need to use the formulation. So if you use a shortcut here, maybe everything will work out. But then, so when we talk about n, what is n? Unit vector normal to the boundary, right? So if I want to draw n here, isn't that n? Now that we are at it, let's have the n for the other boundaries too. We have 4 boundaries, not 2. So these are the n's for the other boundaries. So now, going back to x equal to a, what is n1? n1 is 1, n2? Exactly. So n2 is 0, n1 is 1. And what are we specifying these two? T1, n is what? What is the boundary condition? What traction is there? S, positive or negative? Positive. How about T2? N. 0, right? That's the boundary condition. If it's 0, it doesn't mean that it doesn't matter. It's important, right? So, now putting this back together, this becomes what? Sigma n 1 1, or you can write it if you like, sigma xx. The book drops 1x, I don't like it, please don't do it. Sigma x, it's just not nice for a tensor to just have one index. So whenever you see sigma x in the book, think xx, y, y, y. This is s. So, and here sigma 2 1 or 1 2, as you know, it's the same, is 0. This is the boundary condition. And that's how you go from traction to a stress. Remember I told you we don't have a stress boundary condition, but it's true that in elementary strengths of materials you have seen things, because a lot of things have not been discussed like this. You just put the stress as equal to this and that. But see how we are getting into a stress. This is how. Now put the boundary conditions for top and bottom. Those are traction free. So this is called a fixed boundary condition. I guess you all know that. This is a traction boundary condition. The top and bottom is so-called traction free boundary condition. So let's use the same kind of model and see whether you can actually write it down yourself. I write it quietly as always. So you should head down. Don't look at me, just look back and check. Okay? Go to next page. So the black is for y equal to 0. The red is kind of how it would look like for y equal to b, which is on the top. So answering your question, Tom, at the intersection, it's not really defined. It's neither. You can solve it. So let's get to the solution. No. So you cannot say if it is either or. You have done it for sure numerically before, right? You define this boundary, define the other boundary, and they have a point in common, and it cannot be both. So you don't put equal sign, you just put greater, because you cannot define both.
So like numerically, you do define that point, you want to do that. So that all points have to be defined.
No, you don't define, you just click on the boundary, right? You don't really define at that point. And when you click on the other boundary, that point is also included, right?
At least the first boundary of the left, so that's all points. And if there's a common point on the next boundary, it's use that. Otherwise, it's not solid.
You can select one of the two, but typically, I never dealt with it. I always just put the boundary and never define specifically what will happen at that point and solve it. Typically, when you select a boundary, you just see that boundary highlighted. You never deal with the endpoints. I don't know. So which code are you using? Okay.
It said something about
so maybe this is kind of built in. So it is kind of default. If you choose one, they just use that point. I assume. Yeah. Because analytically, you cannot say this point belongs to this boundary or the other boundary. Yeah. Okay, so now that we have this, any questions about that? So let's look at another problem. The fixed boundary condition and the traction are simple. Try to write the boundary condition for the side which is the slope. I'm sorry. Try to write it down. The only problem is that not everyone is trying to No, so I don't assume that you are concerned. The fixed boundary conditions on the top, those are very similar to the previous problem. It's a good exercise, and your next homework is going to have that anyway.
Do you know anything about the geometry that is on the side of the area?
You don't really need it.
I know the different feature.
Draw the end. So I suggest that what you would do is draw the end. Look at the two components in the exam regulation in order to get into it. Okay, so let me quickly do that before maybe. So I write it in X and Y just. So the boundary conditions look something like that. with the x and y that I have selected. Now, Zach asked me a question which I actually wanted to ask you. Now, everything that you see here, let's say in some boundaries we have boundary condition written in terms of displacement, in some in terms of a stress. What do you do if you want to solve for displacement? In displacement formulation, how do you go from a stress to displacement? But if we have written things in a stress, now that we know the material is linear elastic, we can go from a stress to a strain, right? And from a strain to displacement. And that's what we have to do if we are solving, we are using the so-called displacement formulation. So you'll see that there are two ways to solve problems: displacement and a stress formulation. And solving this 15 equation, 15 unknown, is not as easy as it looks like. So there are lots of tricks how to actually get this to work. And we only focus on two-dimensional case, which is easy, or it's possible actually to write it down, the formulation. Okay, it would be a good idea for you to look at the other boundaries. I probably do one more in the polar coordinate just to make sure that you'll be okay with the homework. So see you on Tuesday.